All right, so welcome everyone. Let's start today's central exercise session. We'll be discussing sheet number 6 today. But before we do so, let me once again point to our chat channel. So if you have any questions, you can go to chat.tum.de and please find this channel here, MA9711-CE. You're welcome to ask any questions you have there. The chat will be moderated, and today's moderator is Tiago. Will you please introduce yourself briefly, Tiago?
Yes, hi, I'm Tiago. I'm a PhD student from the Math department, and I'm also one of the tutors. So maybe you have seen me in the exercise sessions. So I will be the moderator today.
Okay, great. Thanks a lot, Tiago. Before we start with sheet number 6, I have a couple of organizational things I'd like to quickly discuss with you. The first one is this here. So you should already have gotten an email that evaluation for this course starts today or started today. The evaluation will be open until next Monday. So I would be very grateful if you post any feedback that you have, any suggestions that you might have. Of course, you can also let me know those suggestions outside of the feedback if you find the text of the feedback forms is too short for what you want to tell us. Feel free to reach out if there's anything, any comment on the course, any suggestions that you have to make the course a better one. Especially as considering the current circumstances, there is a pretty high probability that we'll have to carry on in a similar way in the summer semester. So if there's anything you would like to have changed, here's your chance to have your voice heard. So please take a few minutes to improve this course and fill in the feedback form. One other organizational thing I'd like to discuss is the Q&As. You might have noticed that we have changed the time for the Q&A slots on Friday from the first to the second round. In the first round, we offered slots at 8 o'clock and at 9:45, and we got the feedback that this collides with some other courses that you have. So we tried to change the times. The new times for the second round were then 13:15 and 1500 on Friday. But those turn out to be not too popular with you. So maybe that is too late. The question is, how can we adapt those times for the third round to maybe suit you better? So I'd like to open that to a vote. I've prepared a little poll here, and I'd just like to start that, give you the option of choosing your favorite times out of these 4. And you can choose more than one. So feel free to choose any time that suits you best. Or if there's anything totally different, if none of these times suits you and you'd rather like, I don't know, times on Thursday or so, then just let us know. Please just write a message to chat or to the Moodle forums, and we consider that for the next round of Q&As. Give you a few more seconds to cast your vote. And I'll stop the voting in 5 seconds. Okay, thanks a lot. I'll just publish the results so that you can also have a look at those results. So the 13:15 slot seems to be quite popular, while the 1500 slot probably is not that popular. So maybe I'll discuss the probability, the possibility of changing that to 1 slot in the morning, 1 slot in the afternoon. I'll have to talk to my tutors for that, of course. And as I said, if you have any entirely other issues with the Friday slots or with the Q&As in general, just let us know. Just write a message so that we know when we set up the next round of Q&As. Okay, thanks a lot for your feedback on that one. Let's close that. The next thing I'd like to point out is exam registration has started. So if you want to participate in the exam for this course, at least if you want to participate in the first take, then you should register on TOM online. The registration is open until January 15th. If you don't register for the exam, you will not be able to take it. On the other hand, you are free to deregister until 1 week before the examination date, so until February 10th. So my advice is obvious. Register now, deregister later if you change your mind. The exam date, as far as I know, is February the 17th. Unfortunately, pretty late at 18:15. The retake is currently scheduled for April the 6th at 11:30. And registration for the retake is not currently possible. That will open on March 8th and close on March 22nd. Because the question is asked fairly often, one quick comment. You are free to only register for the retake. So you don't have to register for the first attempt if you don't plan on taking that one. In particular, you don't have to fail it to be able to do the retake. But if you pass the first attempt, then you can't do a retake anymore. And also the next possible date to take this exam will then be February in a year, so February 2022, after the next round of Math 1 lectures. So there's no retake for this course in the summer term. And speaking of exams, there's one more thing I'd like to do. I'd like to offer a test drive for the Toom exam system. So Toom exam is a system that allows us to take exams remotely. And given the current situation, there is, let's say, some probability that we'll have to switch to that remote option. As announced, I'll let you know whether this happens after the Christmas break. But still, I'd like to offer a test drive so that you can get an idea of how that system works in case we have to use it. The test drive will take place on Monday, the 22nd of December, and I'll open the system from 8 o'clock to 10 o'clock in the evening. So that means starting at 8 o'clock, the test exam would be available, and you have until 10 o'clock in the evening to submit your results if you want to take part. The test exam will be pretty short, so that's not representative of a real exam. It'll just contain 2 small demo problems, real problems though, just to give you an idea of how the system will work and how you can work with the system filling the exam. I'll give you a few more details about Toom exam next week right after the CE class, so a day before the test drive starts. The participation is, of course, completely voluntary. The idea is just to give you an idea, an impression of how the system works, and also for us to be able to collect some feedback from you if there's any problems and see if we can work on those. In particular, the results of this examination will have no influence on the real exam. We'll still make an effort to correct the 2 demo problems if that seems possible. Depends a little on the participation. Again, to give you an idea of how the correction might work and how the exam inspection might work so that you can have a test drive of the whole system before we might have to use that for the real exam. If you want to take part, there will be, again, I will tell you next Monday how this will work in more detail. I'll also put up some manuals on the Moodle page, including a Toom exam submission manual with some details on possible apps that you might use or not use. Otherwise, it will be necessary to register for the exam on Toom Online. So if you want to participate, then please register for the actual exam, the first attempt of this course on Toom Online, until that Monday, 21st of December at 1800. At that time, I will collect the data from Toom exam. And of course, you're free to deregister from the exam afterwards. So if you just wanting to take the test drive, but not the actual exam, then after the 22nd of December, you can always deregister from the exam. Okay, I just need to collect your data to be able to enroll you on the Toom exam submission platform. And to do that, I need your registration on Toom Online. Again, more details will be available on Moodle in the course of this week, and I'll give you an introduction into that system after the CE class next Monday. Okay, so much about that. Tiago, any questions about some of these topics already before we start with the actual CE class?
No, just someone asked if the video will be uploaded, I think, on YouTube later.
Yes, so today there seems to be some problem with YouTube. I can't access YouTube, so I can't start the live stream. But of course, the video is still being recorded. So I'll put it up on YouTube sometime tonight. That's it?
No, a lot of people write here. So one asked for a link for registration.
For Toom Online, so just log into your Toom Online account. That should be available on campus.tum.de. And you just go to your curriculum and you'll find the course. And there should be a link for registration.
And someone told there are 3 exams on Toom Online.
There are 3 exams on Toom Online. So what you will see on Toom Online is probably the exam for this course at Munich. That is the right one. Please register for that one. There's also an exam for this course in Straubing. I think that is not the right one. I'm not going to use that for the test drive. And I guess the retake is also visible, but you shouldn't be able to register for that one. So that may be the 3 exams for this course. Choose the one for Munich campus, please.
And someone asked also if is there an option to participate in another Q&A? For example, this Friday, if you already participated in one 2 weeks ago.
If you already participated, I'll have to lift the restrictions. Yes, but considering that there are still 3 places on Friday, I can of course do that, yes. Okay. So maybe you could send me a quick email as a reminder that I don't forget to do that afterwards, and then I'll lift the restriction after the CE class.
Okay, me or the person who asked?
The person who asked.
Okay.
So there's nothing else. I'd say let's start with the exercise sheet. Otherwise, we can always discuss more questions at the end. Okay, so today's sheet 6. Let's start with 6.1. Battle of the Sexes. So that's a game, a classic game in game theory, where 2 people are making plans for the evening, and their prime concern is spending time together. So if they end up not being together in the evening, then both will be unhappy. However, there's 2 possible attempts. There's 2 possible events they could attend. One is a game of baseball. One is a concert. One of the 2 would enjoy baseball more. The other would enjoy the concert more. But again, their prime concern is being together. And remember, this is in a time before instant communication. So there is no chance that you just shoot the other one a text message. You just have to make up your mind, go to one of these events and hope that you'll meet your potential partner there. And this is modeled as a Biomatrix game. So part A gives you the matrix model and asks you to explain why these valuations make sense. And basically, a Biomatrix game consists of 2 matrices, as the name suggests. One is for the so-called row player, that is AR, and it has 1 row for each possible strategy of the row player and 1 column for each possible strategy of the other player, the column player. So in this case, the strategies are they could either attend baseball, that's a B, or they could attend the concert, that's strategy C. And the same strategies are available to the column player. And depending on the outcome on both choices of strategy, the payoff for both players might be different. We already said their prime concern is spending time together, so they will both be unhappy if they end up at different events. That means if the row player chooses C and the column player chooses B, so we're in this situation here, then there will be no payoff. So a payoff of 0 makes sense here. And of course, that's also true if we end up in this situation here, where again, they attend different events, right? And the same is true for the column player. Also a 2x2 matrix. Basically, the column player chooses the column strategy. And again, if both players choose different strategies, then they are both unhappy and neither gets a payoff. So the column player will also have zeros here. In all other situations, there'd be a positive payoff. And in this model, we just choose to assume that the payoff would be 2 if they end up together. So if both attend a concert, for example, then the row player would rather go to baseball, but if they both end up at the concert and meet, that's still fine. So let's say he'll get a payoff of 2. The column player would prefer the concert. So if they end up meeting at the concert, that is the best possible situation for the column player. So the column player gets a little extra payment. And in this model, I just decided to say the column player gets 3 in that situation. So they are together and at the preferred event, that's a payoff of 3. And for this pair BB, the situation is symmetric in this case. So B is the preferred choice of the row player. So if they end up at the baseball game together, the row player gets a payoff of 3. The column player still gets a positive payoff, and we just make that 2. So basically, the numbers, of course, are more or less arbitrary, but the order of those numbers, that should be reflected in whatever model you come up with. Okay, so that's the explanation for this specific model. Any questions so far?
Someone asked, I already answered, but I don't know, someone asked if they can summarize these two matrices into one, where the different values are separated by a comma.
So that's something that you'll often see. These two matrices are often merged into one, where you just say, I'll write, for example, the row player first. And of course, you have to agree on some order. So it's either always the row player first or the column player first. So if I do the row player first, then you would just write pairs into the entries of that matrix, and that would look like this, yeah? So that's also a possibility. I opted to not do this in this course because we'll only very briefly talk about that topic. And it's always a little confusing if you don't know the order. Sometimes it's row player first, sometimes it's column player first. If you want to do that, then please just make a quick note next to your solution saying the first number refers to the row player, the second to the column player, so that the corrector knows what you were thinking. Any more questions?
There were some questions, but about the exam and the quizzes, so maybe we can see them later.
Maybe you can defer those to the end.
Yeah, okay.
Okay, good. Let's go on with part B. Part B is the question of this game, Battle of the Sexes is a zero-sum game. Now, a zero-sum game, if you remember the definition, means that in every situation, the payoff of the row player and the payoff of the column player always sum up to 0. So in other words, one player gets exactly what the other player has to pay. And of course, that is not true here. For example, if you look at the situation BB, then the payoff for the row player is 3, that for the column player is 2, so the total payoff is 5, and that's not 0. If that was a zero-sum game, then we would have pairs like 3 minus 3 or 2 minus 2 or something like that for all possible entries in the matrix. So this is not a zero-sum game. So no, for example, in the strategy pair BB, the total payoff sum is 3 plus 2. So 3 is for the row player, 2 is for the column player, and the sum is 5 and not 0. And for a zero-sum game, the sum always has to be 0. Okay, let's go right to C. The question in C is, does the game have a Nash equilibria in pure strategies? And if we want to find that out, then let's copy those two matrices once again. Yeah. So a Nash equilibrium means a combination of strategies for the row and the column player, such that none of the two players has an incentive to change his or her strategy. So no one will be better off if one of the players changes the strategy unilaterally. So if they are in that situation, then both are kind of content. So if we have a look at the row player first, then this is the payoff matrix of the row player. Let's say column would play the strategy B. What would the row player choose if he knew that? Well, he has a choice between getting a payoff of 0 and a payoff of 3. So of course you would go for the payoff of 3. So that is a situation where the row player would be content if column plays B. This here is not. So clearly this can never be a Nash equilibrium. But this could be, yeah? So at least from the row player's perspective, this might be an equilibrium. And that's the first point we're going to make here. So if column plays, sorry, B, not C, then row will select B as his best response. On the other hand, if column selects C, then row will always play C as well as his best response to get the payoff of 2 and not 0. So if column plays C, then row will also select C. So this leaves us with two possible candidates for Nash equilibria in pure strategies, namely the pairs BB and the pairs CC. So if both play the same strategy, in other words, that could be a Nash equilibrium, at least as far as the row player is concerned. We haven't discussed the column player yet. Okay, so this is the point of view of the row player. Now let's next look at the column player. So we have already reduced the possible equilibria to these two strategy pairs, so we only have to investigate those. And let's have a look at that. For the pair BB, what happens here? For the column player, BB means we are in this situation here. Now, does the column player have an incentive to change her strategy in that situation? Well, if she did, then she would get a payoff of 0 instead of 2. So no, she will stick to playing B, if the raw player sticks to B, of course. Okay, so in this case, column will not change strategy, as the payoff would reduce if she did. And of course, if you look at the situation in CC, so that means we're here in this point here. Again, if we're asking if the column player would be willing to change strategies unilaterally without the row player changing anything, that means she would move here. So if she changed, she'd get a payoff of 0 instead of 3. And of course, that's not an attractive option. So again, column will not change because payoff would decrease from 3 to 2 to 0, sorry. So that means in both of these situations, BB and CC, neither the row player nor the column player has an incentive to change the strategy. And that means both of those are Nash equilibria. So consequences, both BB and CC are in Nash equilibria in pure strategies. Okay, so Biomatrix Game can very well have more than just one Nash equilibrium. In that case, it's 2 in pure strategies, and we'll later see that there is a different one in mixed strategies as well. Questions so far?
Yes, so a person asked if they can, if they have to provide an explanation. You can just say yes, and then mention.
Sorry, I have a hard time understanding you.
Okay, so wait, can you hear me?
Yeah, it's better.
Okay, so one person asked if they have to provide an explanation, or they can just answer yes, and then mention the equilibria or no.
So usually you will have to provide an explanation, at least in the exam, unless the problem statement explicitly asks you not to. So if it says something like, just write down the result, you do not have to provide a justification or an explanation, then you're of course free to just say yes or no. Usually for problems of this kind, I will want to see an explanation. I don't just want you to guess anything. I also want to see if you know why this is the right answer.
Okay, so next question is the Nash equilibrium the same as optimal strategy?
So in the kind of in Biomatrix games, we kind of have to differentiate that. We didn't even really talk about optimal strategies because that would depend on which player we're talking about. The payoffs of the players might be vastly different. A Nash equilibrium is always characterized by being a pair of mutual best responses. So each strategy is a best response to the other strategy, meaning given that, for example, the row player chooses that strategy, then the column player is best off. So this optimal response is playing the equilibrium strategy and vice versa. So in this sense, yes, it's a pair of optimal strategies, but conditioned on the other one also playing that strategy. For matrix games, so games, zero-sum games, where we only need one matrix to describe the whole game, those two notions do indeed coincide. So an optimal strategy One optimal pair of strategies is then always a Nash equilibrium. We'll talk about that later in, I think in C6.2.
Okay, some more questions. So, is it possible to have all entries in the matrix as Nash equilibria?
Is it possible? So the question is it possible that each pair of strategies is a Nash equilibrium? That is, of course, the case. Just think of the trivial game where the payoff is always 0, regardless of the strategy choice. Yeah, then there is never an incentive to change anything. So every combination of strategies will be a Nash equilibrium. It's a pretty boring game, but still it has the property that you desire.
Next question. For question C, it seems like you calculated the Nash equilibria using the assumption that the players knew what the other chose. Is this assumption given?
Actually, that's not quite true. So what I was doing is I was discussing all possible assumptions. So all possible strategies of the other player. So here, for example, when I analyzed the row player situation, I was first asking, well, what if the column player plays B? What would the best response then be? And then in the next step, so this was this one here, in the next step here, I said, well, what if the column player played C? Then what in that situation would be the best response? And that is what gave me these two candidates. And again, I'm doing the same thing for the column player. So I'm not assuming that column plays B because I go through all those possible cases, right? So for every column that there is, for every strategy that the column player has, I analyze the best response of the row player.
Next one. Should we compute this in the exam?
In this case, so C, yes, I would have expected that you find the two Nash equilibria in C, yes. D is different. So in D, I'm asking for a Nash equilibrium in mixed strategies. For a Biomatrix game, that's not so easy to find usually. So we'll see that in a second. And D, the mixed strategy is given, and I'm just asking you to verify that this is the Nash equilibrium. However, for a matrix game, as we'll see in C6.2, you will be able to compute a Nash equilibrium.
Next one. So is there a mathematical way of showing this? So I don't know what this means.
What? Maybe you could specify what you mean by this. We can pick that up later. Otherwise, maybe I just do D. So we do the mixed strategy first, and then we'll see if there's any more questions on Biomatrix case.
Yeah.
Okay, so let's go to D. The problem statement here is show that the strategy pair where each player chooses their preferred event with a probability of 3/5, 60%, constitutes a Nash equilibrium in mixed strategies. So in particular, what does that mean? Well, that means the row strategy in that Nash equilibrium that we're going to show is a Nash equilibrium is choosing the preferred strategy with a probability of 3/5. Row's preferred strategy is baseball, the first strategy in our order. So his mixed strategy would be 3/5, 2/5. And the column strategy would then be 2/5 and 3/5, because column's preferred event is the concert. That's the second strategy. So there's the higher probability here. Okay, so in other words, we are going to show that this pair of strategies, 3/5, 2/5, and 2/5, 3/5, is a Nash equilibrium. And again, this strategy here is for the row player. And the second one is for the column player. So how do we show that this is a Nash equilibrium? Well, again, we'll have to show that these strategies are mutual best responses. So that means two things. That means given that the row player chooses this strategy, the best response, the optimal thing that column could do to react would be this strategy. And vice versa, given that the column player chooses this strategy, row's best response would then be this. So these are the two things that we have to show. And to do that, we just calculate the payoff for all possible strategies of each player responding to the fixed strategy of the other one. So we'll start with the row player, meaning we'll assume that the column player, Celia, that the column player chooses this fixed strategy here. And then we'll see how the row player should respond to that. Okay, so first, assume the column player chooses the strategy 2/5, 3/5. What is row's best response? And we'll have to show that this here is a best response for the row player. Okay, so what strategies can the row player select? Well, basically there's two choices. So whenever I fix the probability for one of those, then the probability for the other will also be fixed. So there's just one parameter I can choose. So let's say let P be the probability of row playing the strategy B, baseball. Then 1 minus P is the probability of row playing C, concert. How should row select B? Well, let's have a look at row's payoff. So row's payoff is given by the row payoff matrix. If we scroll back a little, we'll see that the row payoff matrix is this one here. So what is the payoff of row in this situation? Well, we have this matrix here. That's the row payoff matrix. And row plays the strategy P and 1 minus P. So we'll have to multiply that on the left to get the linear combination of the two rows. And column plays the strategy 2/5 and 3/5. So we multiply that on the right to get the linear combination of the columns corresponding to that. And that's going to be the payoff. So we just have to compute the result here. So that is, let's do this matrix vector multiplication on the right first. That will yield 6/5, and 2 times 3 is also 6/5. So what we get as a total payoff for the row player is 6/5p plus 6/5 times 1 minus p. And of course, you can see this 6/5p and this 6/5 minus p, those cancel out. So what is left is just 6/5. And that is completely independent of the choice of P. So whatever P the row player chooses doesn't really matter for the result. That means every strategy is good. All strategies are best response because none of the possible strategies would give out a particular advantage. Right? So that means every feasible strategy is a best response to 2/5, 3/5 for Rao. In particular, the strategy given in the Nash equilibrium, 3/5, 2/5, that is a best response. Not the only possible best response, but it is a best response. And that's part one of the proof. So basically what we see here is if column player plays her cards right, then the payoff is already fixed. The Rao player doesn't have any influence on the payoff anymore. Okay, that means this first part worked, right? If we know the column strategy, then the Rao strategy that is given here is surely a best response. And then we have to prove that this also works the other way around. Now, if Rao chooses the strategy given in that equilibrium, 3/5, 2/5, then the other one is a best response for column. And we'll do this in the same way. So now assume Rao plays 3/5, 2/5. What is then column's best response? Again, we'll assume that column plays the strategy like P, 1 minus P, with a value of P that we still have to determine. Then what is the payoff for column? Well, Rao plays 3/5, 2/5, so that is fixed. Then in this case, we have to consider the payoff matrix for column. Remember that was 2, 0, 0, 3, like this one here. And column plays P and 1 minus P. And if you compute that, what do we get? Let's multiply those two here first. That will give 6/5 and 6/5. So that looks pretty similar to what we've seen already. And P, 1 minus P. And again, what we get is 6/5P plus 1 minus P times 6/5. And again, that is equal to 6/5. So if Rao plays this strategy, this here, then whatever column does not matter for her payoff. So again, every feasible strategy is a best response for column to the strategy 3/5, 2/5 of Rao. And that means in particular, the strategy given in the problem statement, 2/5 and 3/5, is a best response. And those two things together then mean each of the two strategies is a best response to the other one. So that is a Nash equilibrium. Each of the strategies in the pair was 3/5, 2/5, and 2/5, 3/5. Is a best response to the other one. And that means we have a Nash equilibrium. Right? No player would change his or her strategy given that the other player does not make a change. Of course, that doesn't mean that is the best possible outcome. As you can see, the payoff in this case is 6/5 for both players. So a little above 1. If they had chosen to both go to a concert or both go to baseball instead of using this mixed strategy, then their expected payoff would be 2 or 3. So for both players, the payoff in the other Nash equilibrium would be better than this one. Yeah, so a Nash equilibrium doesn't mean it's the best possible situation for both players. It just means it's a situation where none of the players has an incentive to change his or her strategy. So, questions about this one?
Yes, many questions. So the first one I didn't get. So how would we compute a Nash equilibrium and mix the strategies without having any strategies given?
So as I mentioned already, in Biomatrix games, you wouldn't. That's why I gave them to you. In matrix games, we'll discuss the questions in the next problem. So I'd just like to defer that question a little, if that's okay.
Second one. Is there a mathematical way to show the Nash equilibrium in pure strategies in C?
Is there a mathematical, well, I would say the way I present it is mathematical, but of course, if you disagree, please let me know what you think is unmathematical about this, and I'll give you another answer.
The next question is, can I prove the optimal mixed strategies by calculating the probabilities with 2 expected utility functions for each player?
2 expected. So in this case, we have 2 utility functions, 1 for each player. I'm not quite sure if that's what you mean. And you will have noticed that I'm using those, right? So here, I'm calculating the payoff for column. So this utility function is different than the one for row. And that's actually important. And in this case, of course, there's some kind of symmetry in these functions. That's why this equilibrium is possible at all, and it looks so nice. Otherwise, it might be harder to come up with an equilibrium, or it might not look that nice, or it might be harder to prove. And of course, one other important point is that we have just 2 possible options here, right? So that enables me in particular to model each possible strategy as P on 1 minus P, just 1 parameter. If there were more than this, if I had 2 or 3 or 4 parameters, then of course this might not be so easy. But I'm not quite sure if that is what you meant. So maybe you can rephrase your question, and we can discuss that later.
Okay, so there are more questions. Should I keep going here?
If there's any interesting questions.
Yeah, there are some that I don't understand. So could you please explain why the chosen strategies for row are written in a matrix in the 1 by 2 and vice versa?
So you probably mean this way here. So the idea here is, this is the payoff matrix for row, right? So the payoff for row depends on the choice of strategies of row and of column. Column chooses basically either one of those 2 columns, or in this case, column puts a weight on each of those columns, right? So for example, let's just copy that here. Okay, so for example, in this situation here, let's say these are the weights for the column player, and that means column puts a weight of 2/5 on the first column and 3/5 on the second column, right? And that means that will govern the payoff. So the total payoff, let's copy that row part. The total payoff for column is then pretty much, or the total payoff given through the strategy choice of column is then pretty much fixed. So if you look here at the first row, what happens is that column chooses this with a probability of 2/5 and this with a probability of 3/5. So the expected payoff in the first row would be 3 times 2/5 plus 0 times 3/5. And in the second row, we'd have 0 times 2/5 plus 2 times 3/5. And as you can see, this is exactly the same thing as multiplying this matrix here with this vector. Right? So that's a matrix vector multiplication, putting weights on the columns. And you might remember that we discussed that multiplying a vector on the right of a matrix is the same thing as a linear combination of the columns of that matrix with these coefficients here. So that's exactly what is happening here. Okay, and now we have the outcome of that game that is given by the weights that column chooses. And of course, row can also choose weights. Row chooses weights on the rows. So these weights here, the P and 1 minus P, these are weights on the rows. So that means row will choose the first row with a probability of P and the second one with a probability of 1 minus P. Okay, so that means the outcome or the payoff in the first column, we went this way, the outcome, the payoff in the first column would then be 3P plus 0 times 1 minus P. And for the second column, we would get 0 times P plus 2 times 1 minus P. Right, so this would be the product of those two vectors here. That's a linear combination of the rows. And we learned that taking a linear combination of the rows of a matrix is possible and multiplying a vector from the left. And of course, that has to be a row vector then, so that this matrix vector product is actually defined. Okay, so this would be the result of this operation. And of course, I'd then have to keep the row vector here. The column vector here on the right. Okay, and whatever you do, now if we're here, for example, we have already combined the columns, and next we're going to combine the rows. Here we have already combined the rows, and next we're going to combine the columns of that result. That will always give you just a real number. And whatever you do will give you the same result. So this and this, if you do the computations, you'll end up having a value of 6/5, as we've seen before. Okay, so in one case, you take in linear combinations of columns. In the other, you take in linear combinations of rows. And we discussed before how to do that. So we're just applying what we've learned so far. I hope that was the question, actually. If it wasn't, then just clarify, please.
Someone asked if there is an example of a strategy that is not a Nash equilibrium.
Yeah, of course. For example, if the row player chooses baseball and the column player chooses concert. Just have a look at the matrices here. So if we are in this situation, that's obviously not a Nash equilibrium because, for example, the row player would want to change to this strategy that gives him a better payoff. And also the column player will want to change to this strategy that gives her a better payoff. So this is not a Nash equilibrium, and neither is this. And of course, there's also non-Nash mixed strategies.
I think some people are confused with the 6/5. So someone asked how can I conclude from the solution of the payoff is equals 6/5 that every feasible strategy is a best response to the other strategy.
Mm-hmm. Okay, so the point here is the payoff is constant. It doesn't depend on P anymore. The 6/5 doesn't really matter. The important point is it's not dependent on P. It does not depend on P. So whatever, in this case, the Rao player, was Rao's payoff, whatever the Rao player does will not change the payoff. And that in turn means whatever he does is optimal because there's no way he can get a better result. That's the best he can get. And he'll get it no matter what he does. If the column player chooses this strategy, that is, of course. Yeah, that all depends on this choice. So if the column player plays this, then Rao player's actions do not influence the result. That's the interesting part here. So everything he does is optimal. That's the point. And same thing for the column player, of course. Yeah, again, what we get here is the result here is always 6/5, always constant, no matter what P is. So whatever the column player does, the result is always the same. Or in other words, every strategy is optimal because there's no way the column player can get a better result. Okay, that's the point I was trying to make.
Yes, I guess the others are about this mixed strategy stuff, so maybe we can wait.
Yeah, maybe let's have a look at 6C2 first and then discuss the mixed strategy stuff once again. Okay, let's have a look at 6.2. So in 6.2, we have a matrix game given. And that means we have a zero-sum game that is usually specified by giving just one matrix. And by convention, that is always the payoff matrix of the column player. That's just a convention that we fixed here in this lecture. It would be equally fine if you did the other convention, but that's what we are going to do in this course. Okay, so this is the payoff matrix of the column player. And that means it's a zero-sum game, so whatever the column player gets, the Rao player will have to pay. So for example, if column chooses strategy 2 and Rao chooses strategy 1, so this column, this Rao, we end up at this point. That will mean column gets a payoff of 5 and Rao will have to pay 5. So Rao's payoff will be -5. Yeah, so this is what characterizes a zero-sum game. And of course, you can see this game is heavily biased because in every possible outcome, the column player always gets a payoff and the Rao player always pays. So there's no way the Rao player will win this. Best he can do is lose as few euros as possible. And in this case, we have to analyze the game. So that means we have to determine the value, the optimal strategies, and the Nash equilibrium. Now, the value of a game, that's a new term for matrix games. The value of a game is the expected payoff in optimal strategies. So if we choose an optimal pair of strategies for both players, the value is the expected payoff in that situation. So if you repeat the game very often, that is the mean payoff of the game. And that gives you an idea of whether the game is biased and by how much. So if the value is positive, that means in the long term, column is going to win more than Rao. If it's negative, then Rao is going to win more than column. If it's 0, then the game is balanced. So in the long term, everybody will come out equal. And that's what we would call a fair game, by the way. If the value is 0, then the game is fair. And please don't confuse this with zero-sum games. So the value, at least as far as we are concerned, is only defined for zero-sum games. Yeah, having a value of 0 is not the same as a zero-sum game. It means more than that. And if you make a guess about the value of this game, I hope you would come to the conclusion that the value is going to be positive because it's biased to favor the column player. in the long term, the column player will win. Surely, so the value is going to be positive. That's the one thing we know before we even start the analysis. Okay, let's talk about optimal strategies. Let's start with those. Now, you may remember, I hope you remember, that there is a way to compute a pair of optimal strategies for matrix games. And please remember that only works for matrix games, not for biomatrix games. And that is by solving linear programs. So the linear program associated to a matrix game with Payoff Matrix A. Let me write down the general form first, and then we'll see how to apply that here. So generally, you would maximize the value I'm calling new. That's going to be the value of the game later on. Subject to the conditions that AX is greater or equal to the all ones vector times new. And subject to the condition that the all ones vector transposed X is 1 and X is non-negative. And what does it all mean? Well, X is going to be the strategy of the column player. So AX is going to be the expected payoff. And it's still going to be a vector. So we'll have one entry for each possible choice of the row player. So that means the ith entry of that vector is the expected payoff if the row player chooses row I and the column player chooses strategy X. Right? And what this constraint here says is, for all the rows, the expected payoff is at least as high as new. And that means whatever the row player does, whatever row he chooses, or whatever combination of rows he chooses, the total payoff will be at least new. So what we are looking for here is that this X is a strategy for the column player that enforces a payoff for a column of at least, yeah, you can't read that, of at least new, right? So whatever row does, column will always at least get new if he chooses that strategy X that is the outcome of that optimization problem. And of course, new, so this value here, is also a variable of that optimization problem. We don't know that beforehand. So that's also part of the optimization, to compute the corresponding value of that new. So we're trying to get the best possible value, the maximum mu, such that we can enforce a payoff of mu at least. And that's what the column player wants to do. The column player wants to maximize her payoff. So she wants to find the maximum mu such that she can enforce a payoff of at least mu. And these two other lines here, these basically just say X is a feasible strategy. So X is not negative. It's all probability, so that's better be non-negative. And this here says the sum of all the entries is equal to 1. So in particular, if we have a sum of non-negative entries that is equal to 1, then none of the entries can be larger than 1. Right? So we have probabilities, they sum up to 100% or to 1. So that's the optimization problem from the point of view of the column player. And of course, there's also an optimization problem for row. Oops. And that looks very similar. Now, row is the player who needs to pay the outcome. So he's interested in minimizing the result. That's why he's looking for a minimum new that he can enforce. And then the rest is symmetric, basically. Now, what the row player needs to do is, if we fix the strategy of the row player to, let's say, a vector y, then we can have a look at y transposed A. And that is then a vector of columns, one for each strategy of a column player, such that if the row player chooses strategy y, then for each column that the column player could choose, we'll have the expected payoff in that column. And what the row player wants to do is he wants to keep that payoff as low as possible. So he wants to enforce a lower payoff, and that means he wants to bound that from above. And again, if he's able to bound that by a value of mu for each column, so this is a vector that has just mu's, column vector that has just mu's, row vector has just mu's in the entries. So that means the row player is able to bound the outcome for each column by mu. So whatever the column player chooses, the payoff will at most be mu. And if that's negative, all the better. Yeah, in that case, the row player would get something. So that is what the row player wants to do. He wants to minimize mu such that he can enforce a payoff of at most mu. Okay, so what this is, it says this y is a strategy for the row player that enforces a payoff, let's again say for column of at most mu. And of course, row is interested in reducing the payoff to column because he's going to pay that. And then, of course, the other two lines are pretty much the same as before. So again, we have the y entries sum up to 1 and y is non-negative. So that again means y is a feasible strategy. Okay, so that's the optimization problem from the point of view of row. And that means if we have a solution to these two problems, then that constitutes a pair of optimal strategies for row and for column. Okay, so much about the general LP. Let's apply that to our specific situation. So what do we get here? If we use this this value for A, this 1, 5, 2, 10. Let's copy that once again. So A is 1, 5, 2, 10. And now we want to apply that for the row player. Let's start with that one. No, for a column player. Let's start with the column player on the left. Column player. Again, the column player maximizes. So we want to maximize new variable. We don't know the value for that yet. Such that, let's see, the column player chooses weights on these columns. So we'll have x1 and x2. And then for the first row, the outcome will be x1, or 1 times x1, plus 5 times x2. And for the second row, the outcome will be 2 times x1 and 10 times x2. And again, the column player wants to maximize the payoff, so he's interested in bounding that here from below. Or both of these, both of these should be at least new. And then, of course, x1 plus x2 is 1, and x is greater or equal to 0. So that's the LP of the column player. And the row player has a similar LP. He's going to minimize the value such that when the row player is assigning values or weights to the rows, such that the payoff of the columns is bounded. So the payoff in this first column is going to be bounded by y1 plus 2, y2. And for the second column, the payoff is going to be 5 y1 plus 10 y2. And in both cases, the row player wants the payoff to be bounded above. So you want that to be bounded by mu from above. And that means whatever a column player does, the payoff can never be higher than mu. And we want to minimize mu for the row player. Okay, and again, we need y1 plus y2 is equal to 1 and y is greater or equal to 0. So those are the two linear programming problems that we need to solve. And every optimal solution for these gives us the right values for x1 and x2. When that's then an optimal strategy, or for y1 and y2, and that's an optimal strategy for the row player. And also the right value for v, and that is going to be the value of the game. And of course, that value has to be the same for both, right? So that new value here, that will coincide for both LPs.
Michael?
Yeah.
Just a second, I think someone said that I'm not sure whether you wrote column instead of row in the max v problem.
In the max problem, so you mean here?
I mean, I think up there, exit strategy for the column, that the force is a payoff for the row.
This one?
Yeah.
That was the payoff for column. Actually, that is correct here. So the payoff for column is bounded by mu above, bounded from above. That means column gets at most mu. That's what I mean here. And row has to pay that. So row is interested in reducing that payoff.
Oh, sorry, the one above, she said.
I could also say it forces the payoff for row to be bounded by minus that value.
Yeah, they're in the max v.
Or did I mix that up here, you mean? It forces a payoff for column? No, same thing. Again, the reason for writing column both times here is that we always compute the payoff from the point of view of column. Right? So the matrix that we have, the matrix A, is the payoff matrix for column. So the payoff that we get using that matrix is, strictly speaking, the payoff for column. The negative of that is the payoff of row. So I could also say minus that would then be the payoff of row. That's the reason for having column both times here. You could easily switch that by just changing the sign. But the payoff is always considered from the point of view of the column player, just by convention. Yeah, we only have one matrix, and by convention, that is column's payoff matrix. That's why the payoff we compute this way is always column's payoff. That's why I wrote column both times, here and here.
Okay. And is this a matrix game is always a sum zero game, or?
A matrix game is always a zero-sum game. Yeah, that's right.
Yeah, okay.
Yes. Yeah, so matrix game by definition means the same thing as zero-sum game. And just by convention, the one matrix that we keep is columns matrix. We could also have done that differently, but we just have to settle on one convention here. Yeah, so in other words, column is always the one who gets the payoff, row is always the one who pays the payoff. And of course, the payoff can be negative. Yeah, so if row is actually receiving a payout, then the payoff will be negative. Okay, does that clarify that confusion a little?
She didn't say anything else, so I hope, yes.
So just follow up on that question if it's still not clear.
Okay.
Okay, so let's see how we can solve this situation. Basically, there's one possibility that always works, and that you know from management science, and would be apply the simplex algorithm. You have two linear programming problems, and you can easily solve, more or less easily solve an LP by applying the simplex algorithm. downside, of course, is that might be quite some machinery, so it might take some time. And in this case, it's probably easier to see the solution in some other way. But you could start with the simplex algorithm here. And actually, in the suggested solutions, I'm also going to do just that. So if you're interested in doing that with the simplex algorithm, feel free to try that for yourself first. Might be a good exercise. And then have a look at the suggested solutions. I'll show you how to solve this using simplex. It's not that complicated in this case. In some cases, these LPs can even be solved, let's say, by inspection, more or less. And that is the case here. So I'm going to show you that way now because it's shorter. But of course, the downside is that will not always work. If the LPs get more complex and larger, then this is bound to fail. And in that case, you will have to resort to the simplex algorithm. So you should know how to do simplex, at least as a backup plan, in case you don't see the shortcut or there is no shortcut. Okay, so let's talk about shortcuts. The one thing, or the one important thing here that enables this shortcut is that we only have 2 strategies for each player. So that means, as before, if I fix the value of x1, for example, then I know x2 will be 1 minus x1. And of course, I can use that to simplify my LPs a little. So what I can do is I can use x1 plus x2 equals 1. And that means x2 is the same as 1 minus x1. And I can do the same thing here. y1 plus y2 is also 1. So y2 is 1 minus y1. And if I do that, the LPs look a little simpler. So I can then say, well, we still maximize. We maximize new. Subject to, let's see. First condition here, x1 plus 5x2. Now, if I write instead x1 plus 5, 1 minus x1 is greater or equal to new, then what I get, or let's also do this for the second constraint here, 2x1 plus 10, 1 minus x1 is greater or equal to new. So I can just take these two. And then, of course, I can add the constraints. x1 has to be non-negative, and x1 has to be less or equal to 1. That's implied by the sum. And if I'm going to get rid of x2, then I have to add this constraint. And I can do the same thing for the minimization problem here. So that's minimize new y1 plus 2, 1 minus y1 is less or equal to new. And 5y1 plus 10, 1 minus y1 is less or equal to new. y1 is greater or equal to 0 and less or equal to 1. Okay, so these look a little simpler. And of course, I can just simplify that a little more. And then I get maximize new. So let's see. So what this says is new is less or equal to x1 plus 5 minus 5x1. So x1 minus 5x1, that's minus 4x1. So we get new is less or equal to 5 minus 4x1. And for the second constraint here, we get 2x1 minus 10x1, that's minus 8x1 plus 10. So new is less or equal to 10 minus 8x1. And again, x1 is between 0 and 1. And I can do the same thing here. I'm going to minimize new here. So I'm interested in lower bounds of new. So I'm going to write this as new is greater or equal to something. And in this case, we have y1 and minus 2y1. So that's minus y1 plus 2. So this first constraint says nu is greater or equal to 2 minus y1. And that second constraint here says nu is greater or equal to 10 plus 5y1 minus 10y1. So that's minus 5y1. 10 minus 5y1. And again, y1 is between 0 and 1. Well, and now in this formulation, you should be able to see the optimal solutions. So we want to find in the left LP, you want to find the maximal possible value of nu and a corresponding value of x1 such that nu is less or equal to this and to this. So if you want to maximize nu, then of course we have to maximize these right-hand sides here. Well, one is when is that right-hand side maximal? Well, x is non-negative, right? So we're subtracting something here. That means if you want to maximize this expression and also this expression, then we have to minimize x1. And the minimum possible value of x1 is 0. So if I substitute 0 for x1 here and here, then this gives me the maximum possible right-hand side and therefore the maximum possible value of nu. Right, so maximum possible nu is achieved for x1 equals 0 as that maximizes both, let's just say right-hand sides in the way I've written them. What I mean is it maximizes the expression 5 minus 4x1 and 10 minus 8x1. Okay, and what are those two expressions? If I substitute x1 equals 0, then I get 5 and I get 10. So the maximum possible value of nu will be 5, right? Nu is then constrained as nu is less or equal to 5 and nu is less or equal to 10. Both have to hold at the same time. So I can't go beyond 5 because that would not hold then anymore. But if I don't go beyond 5, then this is automatically fulfilled. So 5 is the maximum value I can get. Okay, so this will result in a value of nu equals 5 for the optimal solution. Okay, so optimal solution is x1 equals 0. x2 will then have to be 1, and nu is 5. And of course, so I can do the same thing for the minimization problem, this one here. Now this time I would like to get the nu as low as possible. That means I have to get these expressions here as low as possible. And I can do that by choosing the y as high as possible because I'm subtracting that. Okay, so in this case, the minimum possible nu is achieved for y1 equals 1. As that minimizes the two expressions 2 minus y1 and 10 minus 5y1. And in particular, these will then be 1 and 5. And that means nu has to be greater or equal to 1, and it has to be greater or equal to 5 at the same time. So 5 is the lowest possible choice that I can make here. Okay, so that means nu equals 5 is the best possible solution. So my optimal solution here is, y1 equals 1. That means y2 has to be 0. And again, nu has to be 5. So as you can see, the value that nu does in fact coincide here, right? And of course, both players should get the same expected value from their LPs. So that's, so to say, the long-term expected payoff for the column player. In the long term, if the game is played more and more often, the column player will, on average, win 5 per game. So as you can see, as we said already, the game is heavily biased in favor of column. So in summary, we have our optimal solutions. We have an optimal pair of strategies for row and column, and that pair of strategies is the row strategy is 1, 0. The column strategy is 0, 1. Yeah, remember, X is the column strategy. And Y is the row strategy in this notation. So these are the optimal strategies. The value is 5. And this is also a Nash equilibrium in mixed, in pure strategies even, right? If it had been in mixed strategies, that wouldn't have mattered. We also would have gotten that result. In this case, there is even a Nash equilibrium in pure strategies. And of course, before you ask that question, if you see that right at the beginning, that's of course the maximum possible shortcut to this problem here. What we have is, for the optimal strategies, what we found is the, what did we find actually? The row player will choose the first row, the column player will choose the second column. So we end up here and here. So this is our optimum combination. And as you can see at this point, the column player does not want to change, because that would mean the column player only gets 1 instead of 5, and column wants to maximize the output, the payoff. So column is content here in that situation. The row player also would not want to change, because if he did, then he would have to pay 10 instead of just 5. Remember, the row player wants to minimize the payoff because he's going to pay it. Right? So that is a situation where both are content with their strategies, given that the other player doesn't change his or her strategy. So you can easily argue that is a Nash equilibrium in pure strategies. And of course, that means the corresponding strategies are optimal strategies, because we have a matrix game. So optimal strategies and Nash equilibria are the same thing. Okay, so if you discover that, if you argue this is a Nash equilibrium, then right away you have the answer, you have the optimal strategies without solving anything. And that would, of course, be a totally valid answer. Okay, let's see what questions there are. I think I answered every question of the problem statement, right? Yes, I did. Let's see if I can answer your questions as well.
What would happen if we get positive and negative X in the constraints?
Okay, so what would happen if we get positive or negative X's? Like, for example, let's go there. Like if that was a minus and that was a plus, for example, right? Then it would not be that easy anymore. So then, of course, you could say, well, I'm interested in making this here as high as possible, but at the same time making this here as high as possible. And here that would mean minimizing the X, and here would mean maximizing the X. And those are conflicting goals in a way. So it's not so easy to see what the optimum is anymore. So if that happens, your best bet is probably to just start with the simplex algorithm right away. So what I want to say is this shortcut works out so nicely because I specifically tailored the matrix for that, right? If the matrix was different, that might not have worked. And there's not a very good way of seeing upfront if that would work or not. So if you're not sure about this, of course, if it's just a homework, you can always try the shortcut first. In the exam, if you're not too sure that the shortcut will work, then maybe you should right away resort to the simplex algorithm. You could still try to argue around that somehow, but it will get more complicated.
Okay, so the other question is, can I eliminate the strategies in this matrix game because the row player will never play the second strategy and the column player will always play the strategy 2 because his payoff is always better.
Of course, that's also a valid strategy, yeah, right? So in this case, if you look at the rows, you can see that each entry in the first row is strictly less than each entry in the second row. So the row player is always better off playing the first row. That's correct. And the same thing for the column player. Here, each entry in the second column is strictly larger than the entry in the first column. So the column player will always be better off playing the second column. And that means, again, we land on this point here. Yeah. So you can also argue by eliminating strategies why this is, well, the only remaining point, why this is a Nash equilibrium in effect. That's the argument you have made here. And of course, that would also mean you have the optimal strategies, you have the value, you're done. That's fine here. Again, that would work because of the special structure of this matrix. So you could have solved this a lot faster than I did. I was just trying to show you the general way of attacking these kind of problems.
Someone asked, what is the value of this game?
What is the value? The value is 5. So the value is the expected outcome in optimal strategies, the expected payoff in optimal strategies. And if we computed the optimal strategies, remember those were y2 equals 1, so the second column, and x1 equals 1, so the first row. That means the payoff, the expected payoff is then 5, and that's the value of the game.
And I think some people got confused again now. How is v equals 5 the minimum?
How is v equals 5 the minimum? So I guess we're talking about this LP here where we minimize. So remember, we have these two constraints here. We want to find a y1 and the corresponding nu that satisfy these constraints, such that nu is minimized. And if you want to minimize nu, of course, we have to minimize this right-hand side here. And we can do that by setting y1 as high as possible, right? We're subtracting that value, so that will minimize the right-hand sides. So that's why we argued, well, y1 has to be 1. If we do that, then this right-hand side here will be 1, 2 minus 1. And the other one will be 10 minus 5, so 5. And now we're looking for the minimum value of v that fulfills both of these constraints. So of course, I'd have to select 5 here. And that constraint is then automatically satisfied. If I choose anything lower than 5, then this constraint will be not feasible, right? So 5 is the minimum possible value of nu that satisfies both of these constraints. And that's why 5 is the outcome here. I hope that clarified that problem. Otherwise, again, please just ask once more.
Someone asked if you could explain how will the objective function look like?
So the objective function of these LPs is pretty simple. If we look at the general form once again, here it is. So the objective function here is the census maximization. In this case, the objective consists of just this one variable nu, right? So with the numbers we have here, you could also write this in the long form by saying, well, we want to maximize Z equals 0 times x1 plus 0 times x2 plus 1 times nu. That's the objective function for the maximization problem. And the same thing for the minimization problem. You would minimize Z equals 0 times y1 plus 0 times y2 plus 1 times nu. Right? So new is the only variable that actually shows up with a positive coefficient in the objective functions. The x and y's do not enter directly. They only enter indirectly because, of course, through these constraints here, they influence the possible values of new, as we have seen in the solution.
So why are the coefficients in the column player constraints taken out of the rows and not the columns?
So in the column player's constraints here, remember this here is our matrix. Again, what we do is we assign values to the columns. That's what the column player does. He assigns or she assigns values, weights to each column. And then we compute the outcome of these weights on the game. And of course, the outcome always depends on what the row player does too. So what the column player can compute is the outcome of the game for each possible choice of the row player. And that's basically what we do. So we say if the row player chooses row 1, then what is the outcome? Well, the outcome is then x1 plus 5x2. x1 is the weight of the column player for the first column, and x2 is the weight of the column player of the second column, right? Column player assigns weights to the columns. And let's make this a 2 here. So this here is what the outcome would be if the row player chose to play row 1. This here is what the outcome would be if the row player chose to play row 2. And what the column player now does, as she doesn't know what the row player will do, is basically to constrain his options. So what the column player does is choose strategies x1, x2, such that whatever the row player does will at least result in a payoff of new. Whatever strategy he chooses will give a value of at least new. And of course, that is also true if the row player chooses some combination of those two rows, yeah, some weights, some mixed strategy. Then we'll have some weight on this times new plus some weight on this times new. And again, the outcome will at least be new in total. And the column player is interested in finding x values, weights on the columns, such that this can be as high as possible. So that's the payment the column player can enforce, independent of the row player. And of course, the row player will then react to that best possible. Yeah, that's this mini-max problem. And the situation is reversed if we look at this minimization problem here.
Someone asked, how would you recognize when there is a possibility to use a shortcut? When go straight into Simplex?
How would you recognize that? Well, if the LP looked as simple as this, I would probably just try to do the substitution here, then simplify, then have a look at the outcome. And if I would not recognize any good way of determining the optimum here, I would just ditch it all and start anew with a simplex. If the situation is more confusing, if the matrix becomes larger or things like that, then of course that might not be easy to see at all. So if in doubt, I would probably just start with a simplex.
Someone asked if you could please show the first step of the simplex in this example.
If I could show the simplex, again, the simplex is in the suggested solution. So maybe you just refer to those, because to show the first step, I would have to reformulate the problem a little first. But I'm outlining this in the suggested solutions. I'll upload those right after this CE class here. So you can look it up there. And if it's not clear what I'm trying to do there, then please just ask in tutorials or the Q&A sessions, and we'll be happy to explain. But that'll just take some time right now.
And I would ask if you could please explain again how to read the payoff matrix.
That's easy, actually. The payoff matrix here, again, by convention, In a matrix game, that's always the payoff matrix of the column player. So what that says is, well, for each combination of strategies, so it has one row for each strategy of the row player. So the row player has two possible strategies here, and one column for each strategy of a column player. So that also has two possible strategies here. And whatever combination they choose results in one entry of a matrix. So for example, if the row player chooses to play row 2, and the column player chooses to play column 1, then that means we end up in this row and in this column. So this is the entry we end up with. And that's the payment that the column player gets. Again, by convention. In a matrix game, it's always a payoff matrix from the point of view of the column player. So the column player would get 2 if row plays row 2 and column plays column 1. That's how to read that payoff matrix. And if you want that from the point of view of the row player, you'll just have to use -A. That's what the row player would get, or if it's negative, he would pay.
So there are coming a lot of questions now. Are we planning moving forward, or?
I would say so, yeah. Maybe let's discuss 6.3. That's actually a very short one. And then we can see if there's any more important questions that I could answer. Otherwise, I'll be happy to go through the chat later on and see if I can answer your questions. But maybe to complete that exercise sheet, let's move forward to C6.3 first. So C6.3. That's actually a former exam problem. I don't know when we used that, but we used it on some exam a few years ago. So you have a matrix n by n, and that matrix is skew symmetric. And one more information, the n is an odd number. And then we have to show that the determinant of A is then 0. Now what we have to do here is, of course, we first have to know what a skew-symmetric matrix is, and then we have to apply some rules of determinant computations. So the first point is, what does skew-symmetric mean? Well, by definition, you hopefully remember that one. Skew-symmetric means the transpose of the matrix A is equal to -A. Right? Symmetric means the transpose is equal to the matrix. Skew-symmetric means it's equal to negative the matrix. Okay, so that's what we have here. And that, of course, is the same thing as saying -A transpose is equal to A. Just multiply all that by -1. So if we were to compute the determinant of A, then that is the same thing as the determinant of -A transpose, right? Because A is skew-symmetric. And now the interesting part here is the next one. So we now have a matrix that we transpose and that we multiply by -1. And the determinant for that, well, you remember if we change the sign of a single row in a matrix, how does that change the determinant? Well, that changes the determinant by -1, right? So you can just take out a factor of -1 out of a single row, and that's the change you get in the determinant. Same works for the columns. So we're taking out that factor of -1. And in this case, we have the minus in every row of the matrix. So we have to take out a -1 in every row, and each such row changes the determinant, the sign of the determinant. So what we get here is a -1 for each row of the matrix. So we get -1 to the n. times determinant of A transposed. Right? So if you're taking out this minus sign here, you have to do it per row. And for each row, if you change the sign of a single row in the matrix, the sign of the determinant changes as well. Having n rows means we have n such sign changes here. And basically, that's the one trick that you need to apply. -1 to something odd. Remember, this n is odd. So this is 1, 3, 5, 7, 9, whatever. -1 to something odd is always negative. So that's -1. And the determinant of the transposed is equal to the determinant itself. One of the rules of matrix of determinants. So what does that mean? That means we have altogether determinant of A is minus determinant of A. Or, in other words, 2 times the determinant of A is 0. But of course, that can only be true if the determinant itself is 0. Right? And as you have seen, this depends on n being an odd number. This would not have worked that same way for an even number. Okay, so that completes the proof of 6.3. Any questions on that one?
No questions so far. So maybe a minute before writing.
Yeah, maybe let's see if there's any important questions remaining about the other problems or general questions. By the way, for questions about the quizzes, if possible, please just post those to the forum or write an email to our quiz masters. They'll be happy to help you there. It's probably easier for all of us. Or of course, you're also welcome to ask during the tutorial classes.
So in the previous question, someone asked if you could explain again how to come up with the LP. So
how do I come up with the LP? So again, let's look at the one with actual numbers. That's probably easier to comprehend.
Wait, maybe this question before, because it's from this exercise. So, but this was not a proof that the determinant is 0. So for this exercise.
Oh yes, it was. Why would you think it wasn't? Maybe you could clarify that point so I could help you there.
What if n wasn't an odd number?
What if n was an odd number? Well, then this wouldn't work. That's important, of course, yeah? If it's not an odd number, then this proof would not work anymore. If it was an odd number, then what we would get here is determinant of A is equal to determinant of A, and well, we've known that before, so that's not very valuable. The odd is important.
This is the Jacob's theorem, right?
This is, I'm not quite sure. Maybe it is.
I also don't know.
You don't know, yeah, okay. I'm not very good with names of theorems.
Yeah. Yeah, so maybe this LP stuff.
Okay, let's a very quick review of this LP stuff again. Where's my matrix? Here it is. So again, this is the payoff matrix. So that means from column's point of view, what column does when choosing a strategy is assigning weights to the columns, x1 and x2, to the first and to the second column. So what is the outcome of the game if column does that? Well, of course, column doesn't know because he doesn't know what row will play. So the best thing that column can compute is the outcome for every possible strategy of row, and that's what he does. So this here is the outcome of the game if Rao chooses strategy 1. This is the outcome of the game if Rao chooses strategy 2. And what column wants to do is maximize this outcome under all circumstances. So whatever Rao does. And of course, Rao will then do what is best for him, and that is minimizing this outcome. So what column needs to do is, column needs to bound these two expressions from below, in this case by mu. And that will guarantee that the payoff is at least nu, because if Rao chooses strategy 1, then this is the outcome, and this is at least nu. If Rao chooses strategy 2, then this is the outcome, and again, this is at least nu. And if Rao chooses some combination, then this will be some weight times nu plus 1 minus that weight times nu. So again, it will at least be nu, right? And then column is interested in maximizing this guaranteed outcome that she will get. And that's the LP from column's point of view. And as I said, the idea is the same for Rao. So the idea here is that Rao assigns weights to the Raos, of course, y1 and y2. And then Rao can compute the outcome of the game depending on column strategy. So what Rao can do is he can say, well, if column chooses strategy 1, column 1, then this is the outcome. If my strategy is y1, y2. If column chooses column 2, then this is the outcome. And what Rao wants is to minimize this outcome, because Rao is going to pay for that. Right? It's a payoff of columns, so Rao is paying that. So Rao wants to bound these from above, right? He's interested in minimizing these expressions. So he's minimizing this right-hand side. And again, he needs to do that for all possible outcomes. Yeah, because if there is one outcome that is better for column, then of course column will choose that. If all the outcomes are at most giving column a payoff of nu, then it doesn't really matter what column does. Right? In any case, the outcome will be limited to nu. And that is what Rao is interested in, limiting the outcome of the game to this value of nu. And he, of course, wants to minimize that value. So that's the LP for the Rao player. Okay, maybe that will become clearer. If you still didn't get that, have a look at the problems in the homework section of the sheet. There'll be more games, more examples. Personally, I feel that becomes a lot clearer if you have a look at more examples and larger games. Yeah, and hopefully that will clarify the role of these IPs or LPs a little.
Someone asked when this will be uploaded on Moodle?
Right after the C class. I don't think I have anything scheduled right away, so I can get that right away. I'll upload the suggested solutions, and of course this these lecture notes here. The video will take a little longer because I have to edit that first, so sometime tonight.
Okay. Yeah, some people got still confused about this 5 is the optimal max value and minimum value, but maybe we can do it in the Q&A sessions, or?
Yeah, maybe if you're still confused about that, again, have a look at some of the homework problems. There's problems with different values for this new. Try to compute that. I find it becomes clearer if I see more examples. So maybe try that first. And you're welcome to ask at the tutorials. We'll be happy to explain that once more in the tutorials. But I think it's more helpful if you try to look at those other examples yourself first.
Okay, I think I don't see. Someone asked, wait, how you managed to check if we performed well enough on the quizzes so that we get a mock exam for the semester?
Yeah, about the quiz results. We didn't find the time to publish the results yet, but I hope we can do this in the course of this week so that at least for the quizzes that you have already completed, you'll know whether you're still on track for getting a mock exam. I think you are, but I have to consult with my Quizmaster team first. Yeah, you get the preliminary results sometime this week.
Okay.
Okay, so again, as a quick reminder, we'll have the Toom exam submission test drive in about a week, next Tuesday in a week. So if you're interested in taking part in that one, then please remember to register for the exam on TUM Online until next Monday evening. And again, I'll give you more details on the Moodle page sometime this week. And I'll also talk about it a little after next week's CE class so that you know what to expect. Again, it does not have an influence on your actual exam result. It's just meant to give you an impression of how that system works in case we'll have to use it. Okay, so that concludes today's CE session. Thanks a lot to Tiago for moderating the chat.
No problem.
And I see you all in the tutorials, hopefully, or at least next Monday in our next CE, last one before Christmas. So goodbye.